Okay, let us begin with matrices. And the first thing that we encounter when we get into further into matrices is going by the syllabus, of course. It's formulating problem involving solution of three linear simultaneous equation and three unknown as a problem involving the solution of a matrix equation or vice versa. This is something that I will be explaining through this instead of explaining what is written here. Basically, let us say that we have three equations over here. We have three equations, and we also have three unknowns. Okay, so all of these are just variables going on, and basically x, y, and z are variables, and a1, b1, c1, a2, b2, c2, a3, b3, and c3 are basically numbers. And all of these three equations, because this is equation number one, equation number two, equation number three, are equal to some number d1, d2, and d3. The way to write this in a matrix form would be this. Okay, we're just gonna take the constants over here and then put them in order because a1, b1, c1. So basically, this column over here represents the constants of x variables. This column over here represents the constants for y variables, and this column over here represents the constants for z variables. This matrix, a 3 by 3 matrix, will then be multiplied by a column vector x, y, z, okay, which will then result in d1, d2, d3, which is the solution of the three equations. So this is basically the way of transforming three linear equation of three variables into a matrix problem. Now, this is pretty basic. Okay, this is nothing new here. So we're just gonna get into stuff that is, what we have to basically do from here onwards. First of all, we need to understand what these three are. This is something that we study in FP1. Okay, so FP1, we study something called an equation of plane. Okay, so these are three equations of plane. What is this? These are the three equations of plane. So basically, there are three planes, and these are the equation of these three planes. Now, what's gonna happen is for those three planes that do exist. Okay, for the three equations we have, there are three planes, and the three planes that we have, basically, what is going to be happening is that they are going to be meeting each other. Now, the thing that we need to memorize and learn is the unique way that these three planes can meet. So there are different ways, different number of ways that these three interact with each other. The first is case one, which we have, which is basically saying a unique solution, aka the normal case. Okay, so this is basically when the determinant of A is not equal to 0. What is A? A is this matrix over here. This matrix over here, this over here, is called matrix A. Okay? So the matrix of constants is called the matrix A. If the determinant of this matrix is not equal to 0, it will be known as a non-singular matrix. And we will name it one more thing, which is a consistent system. Now, what is a consistent system? We'll go on in detail moving onwards. But just so you know, that whenever the determinant of the matrix A is not equal to 0, that matrix will be known as a non-singular matrix, one. Number two, it will be known as a consistent system. Okay, now what is happening here is that the three planes intersect at one common point. Starting off with, the three planes intersect at one common point, and how are we supposed to imagine this? So, for example, the examiner asked us, what is the examiner asking? The examiner is asking, describe to me, describe to me how these planes interact with each other in a geometrical plane. Okay, so we're supposed to be describing how the planes are interacting to each other in a geometrical plane. Okay, and the best example that I can give you in understanding how the three planes are interacting is imagine a corner of a room where the floor and side walls meet. Okay, so this is like floor. This is like the floor of the room. Hold up. This is the floor of the room. This is, you know, This is one wall, and this is the second wall. So what is happening here is that basically this wall, and this floor is meeting at this point at the very corner of the room, and that corner of the room is basically the intersection point of those three planes. What are the three planes? What are the three planes? Plane number one is the side wall. The two planes are the side walls, and the third plane is the floor. Okay, so those three planes are basically meeting at one common point, and that common point is the point of intersection of those three planes. So basically, at the coordinates of that point, at the coordinates of that point, all three equations will be true. So in other words, let's say I, for example, get a point 1 minus 4 3. Okay, let's say I have this point, and I say this is the point where all three planes are meeting. So when I'm gonna put these points in all three equation, which is x, y, and z. So when I'm gonna put these coordinates in all three equation, the left hand side and the right hand side will be equal, which will show us that this point does in fact lie on all three planes, and in other words, all three planes are meeting at this one singular point. Okay, given that the determinant of matrix A is number one equal to 0, or in other words, it's a non-singular matrix or a consistent system. Am I clear till here? Okay, does everything that I have said or mentioned up until now understandable? Okay, great work. Let's move on. Case number two, no unique solution. Okay, now, what does this mean? Is that if the matrix A's determinant is in fact 0, this means it's a singular matrix. Okay, we are provided or we are working with a singular matrix, and singular matrix basically means that the determinant is 0. Okay. Now, the problem arises is that this case over here where the determinant is 0, there are actually two sub cases for it. Okay, so two sub cases. Okay, either 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 the equations have infinitely many solution. Okay, either the equations have infinitely many solution, or there is no solution at all. Okay, so either there is no solution, or if there is a solution, it's infinite. There is like infinite number, if infinite coordinates that can basically make up the equation come true. Okay, treating these cases as subcase 2a and 2b, we have 2a where there is an infinite number of solutions. This is consistent. Now, coming back to what a consistent system is, a consistent system is when the three equations have at least one solution. Okay, so if it's case 1 where there was a unique solution, in other words, there was only one point of intersection, it's consistent because there is a solution. And if there is infinitely many solution, it is still true. Okay, so it's still a consistent system. So consistent system is a system that has either one or more than one solution. Okay, so both unique solution and infinitely many solution fall under a consistent system. Now, how do these planes meet? Okay, how do the three planes meet? It's in geometric terms known as a sheaf of planes, meaning three planes intersect along a common line. So this is the best image I could come up with to represent what it means. Where you can see that this plane over here is straightened up like this. This is crossing the blue plane, and this is crossing the black plane, and the blue and the red and black plane are meeting at this line and this line. Okay, so this is the line where they're meeting, and this line is inside this blue plane. Okay, so any point on this line, the equations will be true. So any coordinate that lies on this exact line, the equations will come true. So since this line, even though this is a diagram over here, since this line can have infinitely many coordinates, infinitely many coordinate, and I can even prove to you. Even though you will say it looks like a rectangle, there is just this much distance. How can it have infinitely many solutions? So there's like one small technique that we need to learn about maths is that between the number one and between the number two, there exist infinite numbers. Okay, between two numbers, between two discrete numbers in mathematics, you should know that there exist infinitely many numbers. So saying that a line over here has infinitely many coordinates is not wrong. Okay. Moving onwards, when we have subcase 2b, meaning there is no solution, the system is known as inconsistent. Okay, so because there is no solution. Okay, so for consistency or consistent system, there needs to be one or more solution. The geometrical representation could be either of these two. Either it could be a triangular prism or it could be parallel planes. Okay, so triangular prism looks something like this, and if you look at this, you can understand that two planes of the three planes that exist, any two will be meeting each other, but all three will not be meeting each other at the same time. Okay, so there will be solutions for which two of the equations will be true, however, third equation will not be true. So there exist solutions where two will be true, but the third one will not come true. Okay, so a triangular prism looks something like this, and the examiner is actually quite nice over here. The examiner says that if you are unable to explain to me the geometrical representation of the three planes, you can draw them, okay, and you will still get the marks. So if you just draw, you could just say, okay, so the three planes are in a triangular prism and just draw the diagrams, you will still get the full marks if you don't explain the whole thing over here, basically what is happening. Okay, the other way no solution exists is parallel planes, which means that there exist planes which are just stacked on top of each other. So let's say this is a plane over here, and then there is a plane on top of it. Okay, and they are parallel, which means that the direction vector, any direction vector on this plane will be skew for this plane. Okay, any direction vector that exists on this plane will be skewed for this plane. Okay, they will be skew. In other words, they will always have a certain distance between them. They will never meet. Okay, they will be skew lines, in other words. All right, moving onwards, first thing that you need to know, difference between infinite and new solution, because we realize that the only way to realize if there is no solution or infinitely many solution if the determinant of a is equal to 0. What then? Okay, how will we know after we are able to calculate determinant is equal to 0? How will we know if it's infinite solution or no solution? Okay, so there are three things that you need to do. Number one, use Gaussian elimination. Now, what is Gaussian elimination is something that we will be going over. Okay, so you don't, even if you don't understand what Gaussian elimination is, don't have to worry. We will be going over this. Okay. So first of all, use Gaussian elimination. Okay, and assume that you know what Gaussian elimination is and that you have used it. Number two, if you get a mathematically true but useless statement like 0 equals to 0, it's a consistent system. Okay. So mathematically true but useless statement like 0 equals to 0. We do realize 0 equals to 0. 0 is equal to 0. So that is a consistent system. However, if we do get a if we do get a contradiction, something like 0 equals to 5, it's an inconsistent system. Okay. So Gaussian elimination leads to something like 0 equals to 0, consistent, something like 0 equals to 5, inconsistent. Okay, now we are moving towards what a homogeneous system is. Okay, up until now we have been, going over the theoretical area of matrices, and we will continue going over the theoretical area of matrices. Homogeneous system. Homogeneous system is a system of equation that has all of the three equations are equal to zero. So all three plane equations are equal to zero. All three plane equations are equal to zero. Okay. So these homogeneous system have at least one solution, and it is known as a trivial solution. These equations, I'm gonna be saying this again. These equations have at least one solution, and that solution is known as trivial solution, and that trivial solution is x, y, and z all equal zero. Okay, x, y, and z all equal zero. So that is the trivial solution in case all three plane are equal to zero. For non-trivial solution, if the determinant is equal to zero, okay, I'm gonna repeat this again. If the determinant is equal to zero, then for non-trivial solution, you need to realize that there are infinitely many solutions. If the determinant is not equal to zero and the three plane are still equal to zero, there is only one solution, which is x, y, and z equal to zero. But if the determinant is 0 and all three plane equations are equal to 0, then there are infinitely many solutions, including this solution. Am I clear up until this point? Now we have how to solve a system of equation. Now this is very interesting, and I want full attention to this and exactly what I'm about to say. Okay, because I will be solving one question here. Okay, one question, and I'm going to be explaining. This is the best method that I can come up with. Okay, this is like the best, and the best method for solving system of equation that you can find online and someone can explain to you. There are two methods of solving a system of equation. Okay, number one method is Gaussian elimination, and number two method is Gauss-Jordan elimination. Now, what exactly is Gaussian elimination and what exactly is Gauss-Jordan elimination? Okay, they are the same thing. They are the same thing. It's just that the Gauss-Jordan elimination has a few extra steps. Okay, inside of the matrix. Now, what do I mean by that? I will explain. First thing that you need to know is that the amount of solving that is required for both method is essentially same. Okay, so the mindset that one is easier than the other or one requires less working than the other is wrong. Both require essentially the same amount of working, because at the end of the day you are solving three linear equations requiring with three variables. Okay, so you will be doing around the same amount of working, and the initial steps for both methods are same. Okay, they diverge at the end. So initially you will be doing the same thing, and by the end of it you will be doing different things, both requiring the same amount of hard work. Now, moving onwards, allow me to explain to you the best explanation I can provide to you of how Gaussian elimination and Gauss-Jordan elimination work. Okay, and I've marked this down. I've marked this down right over here. If you can see, okay, first, second, third, fourth, fifth, and sixth. Now, what does this mean? Is that for Gaussian elimination, you need to convert this number into a zero first, then you will convert this into a zero, and lastly you will convert this into a zero. Okay, you need to make this number into a zero first, you need to make this number into a zero afterwards, and lastly you need to make this number into a zero. That is the steps, initial steps for Gaussian elimination. Okay? That doesn't give you the answer right away. For Gauss-Jordan elimination, after you are done converting first, second, and third, these three numbers into 0, you will then move on to convert this number into a 0, then this number into a 0, and lastly this number into a 0. So there are a total of 6 number. Okay. Um, 1 second. Now, where was I? I was saying that when you are done converting these three numbers into zeros, you will convert these three numbers into zeros, and that is Gauss Jordan elimination. So for Gaussian elimination, you need to just convert these three, and for Gauss Jordan, you need to convert these three. However, the knowledge of this is only required for you. The syllabus does not require you to know what Gauss Jordan is, what Gaussian elimination is. You don't need to know what these are, but you need to know how to apply them in case you have to solve a system of linear equation. Is that clear? All right, moving on. Okay. So that means that we can apply any method. Okay, so the exam doesn't have requirement that you have to do Gaussian elimination or you have to do Gauss Jordan elimination. No, it doesn't have any requirement like that. We can apply any method we want. It just depends on what you like. Okay, if you like Gauss Jordan, do that. If you like Gaussian elimination, do that. Me personally, I like Gaussian elimination, and the reason I like Gaussian elimination is because I hate drawing matrices. Okay, so this shit sucks, but pretty much why I just go for Gaussian elimination. Anyways, so let us start with Gaussian elimination, and you'll probably get the idea. When I'll introduce you to the concept of Gaussian elimination, it will automatically give you the idea of how to Gauss-Jordan elimination. And hopefully after this session ends, you can try doing this question again using the Gauss-Jordan elimination method, and I would love that. First of all, what are we going to be doing is that we need to convert this into a 0. Okay, how we do that? We are going to be doing something called raw operation. Okay, first of all, we are going to be writing this into an augmented matrix. Okay, we converted this into an augmented matrix. How we did that? You can see this. The first column is going to be going to be basically the column of constants for x. The second column is going to be the column of constant of y, and the third column is going to be the column of constants of z. Okay, and the last column is going to be our answer column, the solution column, 3 0 minus 1. Once we are done converting this three equation into an augmented matrix, we are going to be doing something called raw operations. Raw operations are basically that you can subtract raws from each other. So yeah, you can subtract raws from each other, first of all. Secondly, you can multiply a number to a raw. Okay, now you need to know this is actually something that I should tell you and you should realize, is that in raw operations, because mathematicians, they are sometimes very stinky about these things. In raw operations, you can't divide a raw with a number. You will never be dividing a raw with a number. You will always multiply. Okay, so how to bypass that? Let us say we want to divide a raw by number 3. We're just gonna say multiplied by 1 over 3. Okay, so I know sounds crazy. We can just say divide by 3, but mathematicians, what can I say? I'm not one. Anyways, point is that you can add two raws together. You can multiply a number with a raw. However, you cannot divide a number with a raw. So in order to divide a number which is multiplied by its reciprocal, so I want to divide a number by 5, I will instead do multiplied by 1 over 5. Now, this is going to be short, and I think there are some raw operations that will be discussed further ahead as well, so you can know what I'm talking about. Let us say we had to convert this number into a 0. What I'm going to do is that, okay, make sure to listen to this very carefully. What I'm going to do is that I'm going to subtract raw 3. This is a raw. I'm going to be subtracting raw 3 from raw 1. Okay, I'm going to be subtracting raw 3 from raw 1. Okay, so in other words, raw 3 or raw 3 minus raw 1 or raw 1 minus raw 3, same thing, it doesn't really matter as long as you do it right. So raw 3 minus raw 1 uh, will be 1 minus 1 equal to 0. Okay, we have to first write the raw that we are changing. We are changing raw 3, and raw 3 is becoming raw 3 minus 1. Raw 3 is now becoming raw 3 minus 1. Okay, so 1 minus 1 is 0, 2 minus 1 is 1, minus 3 minus 2 is minus 5. There we go. And minus 4 minus 3 is minus 7. Okay, this is the first raw operation I did. Okay, you cannot do two raw operation on a raw at the same time. So I just did one, and then the second one I did is on raw two. Okay, what did I do with raw two? Since I had to convert this into a zero as well, since I had to convert this into a zero as well, what I did was that I first, okay, in my mind converted this raw by multiplying this raw by 2. Why did I do that is so that we get a 2 over here. When we have a 2 over here, that 2 is going to be subtracted from this 2 to result in 0. This is a bit confusing, I am aware. Okay, allow me to explain again. First, let me confirm, is there any issue with this raw operation? The second raw operation is basically me subtracting raw 2 by 2 multiplied by raw 1. Okay, raw 2 subtracted by 2 multiplied by raw 1. Okay, so what I'm going to do, I'm going to pick up, you don't really need a calculator, just need to use brain. So 2 minus 2 multiplied by 1 minus 1 minus 2 multiplied by 2. So what I'm doing is just 2 minus 2 multiplied by 1 minus 1 minus 2 multiplied by 1, and then minus 1 minus 2 multiplied by 2, and then 0 minus 2 multiplied by 3. Did that make sense? After we are done, we will see that this, if we do the calculation for all these four number of this second raw, we will get these four number. Okay, now that we have these four numbers, we are done with converting these two into zeros, and we are just left with this. Okay, we have to convert this into 0. How are we going to do that? How are we going to do that? Is first of all, my bad. We have to convert this into 0. Sorry about that. We have to convert this into 0. Okay. How are we going to do that? Is what this is a very crucial step. Okay, so the crucial step is, first of all, you need to convert this into 1. Listen very carefully. We have to first convert this into 1. We have to convert this into 1. Okay, how are we going to convert this into 1? Is by dividing this number by minus 3. Since we cannot divide, we are instead going to multiply it by minus 1 over 3, or negative 1 over 3. Now, what happens when we multiply this by negative 1 over 3? It becomes 1. Amazing. It becomes 5 over 3. Great. It becomes 2. Cinema. Moving onwards. The next thing that we need to do is, when we have 1 over here, we have this number converted into a 1. What we are going to do is, we are now going to subtract raw 3 from this new raw 2. Subtract raw 3 from this new raw 2. Okay, so 0 minus 0 is 0, 1 minus 1 is 0, minus 5 over 3 is 20, minus 20 over 3, minus 7 minus 2 is minus 9. Okay, now that we have converted these three numbers into 0, we are left with this. Was that understandable? Now that we are done here, okay, now we can find the values for x, y, and z. So this column was for variable z, which means minus 20 over 3z is now equals to minus 9. So minus 20 over z, minus 20 over 3z is now equal to minus 9, and if we solve this, we get z equals to 27 over 20. Okay, if we're going from top to up, okay, using this, we were able to find z, and now we're going to use this. What does this say? This says y plus 5 over 3z is equals to 2. Okay, so y plus 5 over 3z is equal to 2. And what we're going to do is we're going to input the value of z in this. Okay, we are going to input the value of z in this. Okay, so this is being subtracted over here. This is, as you can see, being subtracted. When it's going to be moved here, it is going to be minus 5 over 3z. That is what I did. I moved it here, it became minus 5 over 3, and I replaced the value of z with 27 over 20, and then I just solved this thing. We got negative 1 over 4. Now, using the values for y and z, we are going to find x by this equation. Okay? So, what does this equation say? It says x plus y plus 2z is equals to 3. So, x plus y plus 2z is equal to 3. X minus 1 over 4 plus 2 into 27 over 20 is equal to 3. Then we solve and we get the value of x is 11 over 20. Now we have all three values. Was that easy to understand? Let us move on to solving homogeneous system of linear equation for non-trivial solution, if possible. Okay, if possible basically means to take determinant of this. We are going to be taking the determinant of this and see if it is non-zero. If the determinant of matrix A is non-zero, we are going to calculate a non-trivial solution. Now this is very important and this is a bit confusing as well, so make sure you're listening very carefully. If you look at the raw operations I've done here, okay, since this is basically zero, we absolutely just ignore this. Okay, so for homogeneous equation, we're just going to ignore this column. It's going to be looking at this. We just look at this. We completely ignore this. And we are going to do some raw operations. Now, notice, if you notice, and I hope you're noticing that while I was trying to do raw operations, I accidentally made this raw into zero. Okay, I'm about to answer your previous question. This is about to answer your previous question. Okay, must be some prophecy that it became all zero. Now, while I was doing raw operations, you can see that this becomes entirely zero. That is something that we need to do to find the non-trivial solution. There is something that we need to do to find the non-trivial solution. Now, what is that thing? What exactly is that hidden power that we need to pull out in order to find the non-trivial solution? Okay, first of all, allow me to just correct this absolute mistake that I've made here. Okay, there we go. Now, that hidden power is that we are going to be taking this equation over here because we know that everything was equal to zero. So this equation over here, which will be minus 3z plus 9y, will be equal to zero right over here. Okay, and what we are going to do is that we are going to assume that z is equal to some number 3. Okay, so for z is equals to t, z is equals to t, y is equals to 3t, which is, why is that? Because minus 3y plus 9z is equals to 0. This goes here to become positive 3y. We're going to divide both sides by 3. We got 3z is equals to y. Since we change z with a t, so y is now equals to 3t. Okay, now that we know the value of y and value of z, these are the values of y and values of z. We are going to use this value in this equation over here in the top equation. Okay, so the top equation was x plus 2y minus 2z is equal to 0. We're gonna change y with 3t and we're gonna change z with t, and then we're gonna calculate x. We will get x equals to minus 4t, and these are our values. These are the three values for our homogeneous, non-trivial solution of a consistent system. Was that understandable? Okay, we are now moving on towards the real stuff. Okay, the real shit. Okay, realist shit in matrices out there. Uh, Understand the blah 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 whatever. Basically, something called eigenvalues and eigenvectors. Okay. Now I have provided a written description of what it is, and I'm going to be reading it to you. So don't sleep. Eigenvector is a special non-zero vector that, when put through the transformation, does not change its direction, only stretched. Wow, what does this mean? This means that, let us say that we have a 3 by 3 matrix, 3 by 3 matrix over here, okay, and then assume that this is a transformation matrix, and then we have a vector over here, okay, we have a vector over here. We multiplied this transformation matrix with this vector, and the answer we get is some number multiplied by this vector. Okay, so when we apply this transformation onto this vector, we will get the same vector but multiplied by some number. So in other words, let us say that we had a vector I plus 2j minus 3k. It will become something like 2I plus 4j minus 6k, or something like minus 3I minus 6j plus 9k. So over here, what happened was that this one got multiplied by 2 and this one got multiplied by negative 3. However, it is still the same vector, just multiplied by some number, which means that it was stretched. It was only stretched, but nothing really happened. Okay. Now, it didn't, like, go round and round and blah blah blah. The angle was basically the same. You understand it, it makes sense what I'm trying to say. I'll still show you one more thing just in case. So basically, let us say our vector was something like this. It was making an angle with the x-axis of, let us say, 45 degree. So after transformation, it is still going to be making the same angle. That is what it means to keep the direction. That is what it means that direction does not change. Direction does not change essentially means that it is still going to be making the same angle with the x-axis it was originally making. Was it easier to understand? Moving onwards, how do we find eigenvalues and eigenvectors? Okay, I'm about to provide you with the ultimate stuff here. Okay, peak quality, better than drugs, by the way. Eigenvalues and eigenvectors stuff. Okay, so we have a matrix A, and we are asked or tasked to find its eigenvalues and eigenvectors. Now, how do we do that? How are we going to be doing that? Is first of all, let us come back here and study something over here. Okay. If I zoom in a bit more, okay, never mind. I can't zoom in a bit more. Okay, I can. If I zoom in a bit more, matrix A is being multiplied by the eigenvector, which results in a number multiplied by the eigenvector. Okay. This number, this stretch factor, this number that is going to be stretching this vector is called eigenvalue. Okay. These vector, the vector to which the matrix is being multiplied to, is called the eigenvector, and this matrix is called a transformation matrix. Okay. Now, since these two are equal to each other, if I bring this over to this side, it is going to get subtracted from this, and if I take v common, we get this equation. Now, something that you need to understand, you'll be like, oh, where did this I come from? Where did this I come from? Let me tell you. This A is a matrix. This lambda is a number. For a matrix to be subtracted by a number, that number must be multiplied by I. In other words, the identity matrix. And that identity matrix for a 3 by 3 matrix is 1 0 0 0 1 0 0 0 1. This is the identity matrix. Okay, so that lambda value is essentially being multiplied with this. All right. So we have this. Okay, and since we know that this actually equals to 0, when we take the determinant of this, okay, we're just gonna basically join this out of here. If we take the determinant of this, okay, I'm gonna explain why we join it. It's because if two numbers are multiplying and they're resulting in 0, one of them must be 0. Okay, for any two numbers that are multiplying together and result in a 0, one of the numbers must be 0. Since the vector is not 0, because vector exists, we know the vector exists. Since the vector is not 0, this means that this is 0. And how is this 0? We're gonna find the determinant and say the determinant of this exact thing is equal to 0. Oops. This thing is called a characteristic equation and we are going to be using it. Okay. Wow, that's a lot of things that I talked about. Moving onwards. How do we find eigenvalues and eigenvectors? First thing that we need to do is, easier said, easier shown, easy to uh, easy to show basically, is that from this transformation matrix over here, we are going to subtract lambda from the main diagonal. From the main diagonal, we'll subtract lambda. Lambda will be subtracted from 2, lambda will be subtracted from 3, and lambda will be subtracted from 1. Okay, so essentially, I've shown here is that A minus lambda into identity matrix is basically A subtracted by identity matrix with the ones replaced by lambda, which then results in this matrix. Now, this is a rule that the exam requires you to remember. Okay, so this is a rule that you must in your exam remember. What is the rule? The rule is that if A is an upper triangle matrix, for any triangular matrix, eigenvalues are simply the numbers on the main diagonal. Wow! What does this mean? It means that if these three are 0, or if these three are 0, it is a triangular matrix. Okay? And the eigenvalues, how to find the eigenvalues of a triangular matrix, in other words, a matrix where these three or these three are 0, we will multiply these three together. That is exactly what I mean. And then we'll just find the values of lambda. So lambda is either going to be 2 equals to lambda, 3 equals to lambda, or 1 equals to lambda. So we will get three values of lambda, 2, 3, and 1. Am I understandable up until this point? Moving onwards. Okay. What we are going to be doing now, we are going to use this matrix over here that we made, okay, this exact matrix over here. And for lambda equals to 2, okay, so for lambda equals to 2, this matrix will be transformed. Okay, we are going to subtract 2 from the main diagonal. Okay, so when we will subtract 2 from this main diagonal, this matrix will transform into becoming this matrix right over here. Okay. Now I've written some stuff over here. We are supposed to pick two rows. We are supposed to pick two rows, and those two rows will going to be pick two rows, ignore rows that are same or multiples of each other. Okay, so these two rows are same. We are going to be picking one row from here and the third row. Okay, now, why are we picking two rows? We are supposed to pick two rows. Why are we doing that? Is because we are going to be finding the vector product of those two rows. And the vector product of those two rows will be the eigenvector. Absolute cinema. Alright. Uh, is that clear? Is that clear? So basically the resultant vector over here, the resultant vector after we are done finding the vector product, is essentially the eigenvector. Now, what I did is something called simplification. We should and we can simplify eigenvector. Is that since the vector -1, so this is just a vector that is just -1. So a vector -1 and a vector 1 are basically the same thing. So I'm just going to write it as 1 instead. However, if you write it as 1, it's not a problem. It's essentially the same thing. Okay. Moving onwards, for lambda equals to 3, so if I put lambda equals to 3, we get this matrix. But what I did is essentially subtracted lambda from the main diagonal. So 2 minus 3, or subtracted 3 from the main diagonal. So 2 minus 3, 3 minus 3, and 1 minus 3. Now that I have this matrix, once again, we are supposed to pick any two rows. However, raw 3 is just -2 or -2 multiplied by raw 2. So either pick raw 3 or raw 2. So these two are equal to each other. These two are multiples of each other. Raw 2 multiplied by -2 will equal raw 3, or raw 3 divided by -2 will equal raw 2. Okay, so we have to pick either of these rows. So all I did was pick raw 2, and then I'm free to pick raw 1. So raw 1 and raw 2 will be picked, and then I will find the vector product of these two. I will find the vector product, and the vector product is 1 1 0. Vector product gave me the resultant vector, which is 1 1 0. Now, moving on to lambda equals to 1. When we get lambda equals to 1, when we put lambda equals to 1 in this, 2 minus 1, 3 minus 1, 1 minus 1, we will get this matrix over here. What? Where was I? So for lambda equals to 0, we will get this matrix, and a row with all zeros will be ignored. So we'll just have to select these two rows. We are forced to select these two rows because a row with all zeros will have to be ignored. And then when we select these two rows, we just find the vector product. We get something like -1, -1, and 2. And if I simplify this, essentially just change their sign, it becomes -1, 1 minus 2. Which just nothing, okay? It doesn't really do anything. It's just for my own satisfaction because this looks cleaner than this, okay? Everyone has their preferences. Now, what we just learned was how to find number one eigenvalues and number two eigenvectors. Okay, I'm gonna move on. Okay, and we are provided with a new question. This time we are not given a matrix which is triangular matrix like over here. So what we have to do is first of all subtract. Okay, this is something that you can read when the notes are provided to you. So this is something I'm not gonna go over. Okay, this is something extra that you can read and basically understand and learn yourself stuff. So first of all, we know that we have to subtract lambda from the main diagonal. That is exactly what we are going to do. Okay, we are going to subtract lambda from the main diagonal and take the determinant. Okay. So this is us taking the determinant, and this is just the calculation for determinant, leaving us with this equation. This is very, 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 what again? Very, very algebraic coded. So make sure you don't make any mistakes. All right. Um, Moving onwards. I assume there is no problem in this calculation apart from the fact that it is not neat and clean. It is a lot of algebra because this is just us taking the determinant for this matrix over here. Okay, moving onwards. Um, So this is not discussed right now. You can just look at it in the PDF. This is essentially the shortcut way, and the shortcut way calculation is done here. But however, this is not part of the syllabus, so you have to do this entire calculation, the algebraic working over here. Now, when we have found this equation, what we are going to do is solve it. Okay, so geniuses, pick up your calculator and use the feature for solving a cubic equation. Okay, so everyone has different calculators. I hope you do know what your calculator does and how it works and how you can solve a cubic equation in your calculator. Okay, and when you know how to solve a cubic equation in your calculator, you'll be able to solve this equation. And something that I should tell you over here is that you will get three values. Okay, you will get three values, and one thing that you need to realize about those three values is that you won't just write like, oh, so lambda is equals to 1, 2, and 3. No, you're supposed to actually show this. You're supposed to write it like this first. Lambda minus 1, lambda minus, oops, lambda minus 2, and lambda minus 3. Supposed to write this and then convert it into this. You will then convert it into this. Okay? So exactly what is written over here. And I use convert. Now that we have three values for lambda, what we are going to be doing is we subtract each value from this matrix over here, the original matrix, one by one. So for lambda equals to 1, subtract 1 from this equation over here. So 8 minus 1 minus 3 minus 1 and 1 minus 1. When we do that, we get this. Okay. Now, a side note, it's better to pick the raw with more zeros than any other raw. However, don't forget to ignore the 3 0 raw and 1 another, which essentially means is that see this row has a 0. Okay, so we are going to pick this row over here, keeping in mind that it shouldn't be a multiplicative of any other row. However, any row with a 0, this is something that you need to know and something that you need to process in your brain over here. Any row with a 0 will never be a multiple of any other row. So this row has 1 0 and no other row has a 0. So this means that this can never be a multiple of any other row. So we are free to pick this row and free to pick any other row. Exactly what we did. We got this answer. Okay, so as you can see, these three values can be divided by minus 2. These three values can be divided by minus 2. Exactly what I did, and we got our first eigenvector. Is that understandable? Moving onwards. So for lambda equals to 2, essentially we are going to be subtracting 2 from this matrix now. We will get this, and then we can just pick any two rows, find the vector product. This is what we got. I changed the sign to make it this. Lambda equals to 3. This is what we get. Pick any two rows, find the vector product. We get this. Divide by 4 because all these numbers are a multiple of 4. We get the third eigenvector. Now we have found two things. We were able to find eigenvalues, we were able to find eigenvectors. One last step is remaining, which is called diagonalization of a matrix. How to diagonalize a matrix? Okay. How to diagonalize a matrix? For your answer in question number 2, find a matrix P and a matrix Q such that a to the power of n is equals to p multiplied by d to the power of n multiplied by p inverse. All right. Okay. How do we find a matrix? So basically this. So diagonalization. What is the purpose of diagonalization? Is to find higher powers of matrix A. The purpose of diagonalization is to find the higher powers of the matrix A. What do I mean by that? What I mean is basically, let us say you have to find A squared. Very easy to find A squared. However, what if you have to find A to the power of 100? You will not be able to. Okay, so essentially what we do is something called diagonalization, and it is actually very easy. Up until now, the whole thing that we have done is the things that we need to do in order to find our diagonal matrix or matrix D. Okay, so the first thing that we need to do is find values of lambda, and the second thing that we need to do is find the eigenvectors. Okay, now what you're going to do is you're going to put all three eigenvectors, you're going to align, you're going to put them in rows: eigenvector 1, eigenvector 2, and eigenvector 3. We're just going to put the all of three eigenvectors, and the next thing that you're going to do is you're going to make a matrix, diagonal matrix, and this is the eigenvalue for eigenvector 1. This is the eigenvalue for eigenvector 2. This is the eigenvalue for eigenvector 3. Okay, so just it's the same format. You just have to follow this format. All the working is for finding the eigenvalue and eigenvectors. Once you're done finding eigenvalues and eigenvectors, what you're going to do is essentially just put them in a matrix. So eigenvector 1, eigenvector 2, and eigenvector 3. Okay, so and then what you're going to do is lambda for eigenvector 1, lambda for eigenvector 2, and then lambda for eigenvector 3. Essentially, the value of lambda, the order matters a little bit, 50-50. Essentially, if you put eigenvector 2 in place of eigenvector 1, you're going to be putting lambda of vector 2 here and then lambda of vector 1 here. Okay, so the order of these matter. In other words, if I do something like this, I first write lambda 1, then write lambda, I first write eigenvector 1, then eigenvector 3, and then eigenvector 2. My diagonal matrix should have lambda for v1, and then lambda for v3, and then lambda for v2. Okay, so order matters in this way. Okay, so order matters in this sense. However, the 1 2 3 3 2 1 1 3 2, it can be anything. That order doesn't matter. Hopefully that was understandable. If you look at the question, you are essentially being asked matrix P and matrix D. Okay, so that is exactly what you have to find. You don't need to find P inverse. You do not need to find P inverse. The other thing that you need to know is if the question had instead said, find a matrix P and D such that A squared is equals to P D squared P inverse. What we would have done then, The square will not be here, it would just be d. So the square would be here. You have to notice this. You have to notice the power on a. You have to notice the power on a. Okay. So what we would have done then is we would have just squared, because if you look over here, the power on a is 2. We would just square the values of d. Okay, so we will just square these values. We don't have to do anything to p. P will remain same. We will find D like this, and then we will find a new D where it would just be the square of these values. Moving onwards. Okay, we now know how to find this. Alright. Some questions are over here. These questions are non-conventional questions, by the way. Non-conventional questions. In other words, these are questions that will get tested for around 1 to 3 marks in a big question. So you get like a 7 to 11 marks worth of question for matrices, and in that question, 1 to 3 mark question can be something like this. Okay, so we're gonna go them over one by one. The system of linear equations represented by mx is equals to c describes three planes that intersect into form a triangular prism. We need to know that triangular prism is when determinant of A is equal to 0. There is no solution, and it is inconsistent. Okay, it is inconsistent. State with a brief geometrical justification the value of determinant. So the justification is written down below. It says determinant will be 0. Planes form a common line in pairs but have no single point of intersection. Therefore, there is no unique solution. And since there is no unique solution, the matrix M will be singular. And since the matrix M is singular, it means the determinant will be 0. Second question. A 3 by 3 matrix has an eigenvalue lambda with corresponding eigenvector v. Using this definition, show that v is an eigenvector of this equation and state its corresponding eigenvalue. Now, something that you need to know over here, if I just move on, is this equation is something that we discussed at the very start, and they are saying that if, according to this equation and according to lambda, if the eigenvalue is lambda, and for the eigenvalue lambda, we have a eigenvector v. So for eigenvalue lambda, we have a eigenvector v. What they're asking us is that show that for this matrix, when we solve this to get some value of matrix, for this matrix over here, the eigenvector will still be v, and they're asking us the value of lambda for this eigenvector. One thing that I should tell you, however, it is always asked to be proved. Okay. That thing that I'm about to tell you is that whatever transformation happens on a matrix, the eigenvector remains the same. So if A's eigenvector is V, and A went through a transformation this matrix, this new matrix that will be formed by transforming this matrix A, will also have the eigenvector V, just for a different eigenvalue. Hopefully that is easier to understand. Now the whole thing is written over here. For V to be a eigenvector of both A and the equation, we substitute A for lambda to find the eigenvalue of V if V is also an eigenvector. to this. Why lambda? Because lambda was its eigenvalue when it's a eigenvector to A. So essentially, to find the value of lambda, for which V is also an eigenvector for this equation, we just substitute lambda into this equation in place of A. And that equation, which is this equation, is going to be this equation. This is the equation for, oh, sorry, I'm going to remove this. This is going to be the equation for lambda. Okay, this is going to be the equation to find the eigenvalue for which V is also an eigenvector to this equation. And I'm going to be talking a little bit about this question further ahead because there was an exam question that I need to discuss as well. Moving onwards, we have one more question. Okay, and this is just that if 2 by 2 can be diagonalized like this with d is equal to this, state with reason whether b to the power of n approaches a limit matrix. So limit matrix basically means that no visible difference in values when you increase power anymore. So we just essentially give these values a power so high, that going any higher wouldn't make any more difference to their values. Now, will it reach a limit matrix or not? So what I did is that I just put the power n on the matrix. It's basically the same as putting power n on these two numbers. As n reaches infinity, this number becomes 0. However, this number becomes infinity because any number which is a um, fractional number will become 0 when its power is infinity. However, any number that is not a fractional number will not become 0; it will just become something infinity. This shows that for n reaching infinity, this will diverge instead of converging. Diverging means that it will reach some number infinity, and since it reaches some number infinity, it doesn't converge, it doesn't stop. It means that it doesn't reach the limit matrix. Alright. The characteristic equation of a non-singular 3 by 3 matrix is by using the property that a square matrix satisfies its own characteristic equation. Okay, this is an exam question by the way, important. Express C inverse in this form where P, Q, R are constant to be found. Now, we need to find C inverse. So I'm just gonna actually solve it to show you the solving step of what I'm actually doing. Okay. Since C will satisfy its own characteristic equation, we are going to be changing lambda with C. Oops. And when we put, okay, this is going to be 7C. Oh, sorry. When we have no number to put here, because this is transformed into a matrix now, and this is a constant, so we're going to be putting an identity matrix. Now, what we need to do is find C inverse and express it in terms of other C matrices. How will we do that? Very easy. First of all, what we need to do is multiply this entire equation by C inverse. We are going to be multiplying this entire equation by C inverse. When we do that, we will discover that the power of each C matrix will reduce. So C to the power of 3 will just become C squared, C to the power of 2 will just become C, and C will become an identity matrix while the identity matrix will become C inverse. When we have this equation on our hands, what we are going to be doing is rearrange to get C inverse as our to one side, and then get everything to the other side. Okay, so we are going to be expressing everything else. Oh, we are going to be expressing C inverse in terms of everything else given over here. To, and then we can just find C inverse. So we can see that the value is C square P, which is negative 1 over 7. Value with C is Q, which is 5 over 7. Value with I is R, which is negative 2 over 7. A 3 by 3 matrix P has distinct real eigenvalues 4, 2, and 0 determined with justification by the system equation represents three planes meeting at a single unique point. Okay. Now, something that you guys need to know is that the product of eigenvalue is determinant of the matrix. So if P's eigenvalues are 4, 2, and 0, and we multiply them together, it will give us the determinant of P. Okay, so that is exactly what I did. I multiplied these numbers 4, 2, and 0 and got 0. So this 0 is basically the determinant of P, and since P's determinant is 0, it means that P is singular and does not have a unique solution. Was that easier to understand? Moving on to an interesting question we have here. Okay, I hope you guys understand. I'm just really gonna just do the working again. It is given that lambda is an eigenvalue of a non-singular. So what does non-singular mean? What does non-singular mean, chat? Chat, it means the determinant of A is essentially is not equal to 0. It could be less than 0. So sorry about that. It is not equal to 0. Okay. With corresponding eigenvector V. So it has an eigenvector V. Show that E is an eigenvector. And we discussed this about. What did we discuss? Is that no matter what transformation A goes through, if its eigenvector is E, it will still remain E for a different value of lambda. And we are about to show this. We know the equation which says A into eigenvector is equals to lambda into eigenvector. My PC is dying right now. Anyways. And since the eigenvector is E, it's going to become A into E is equals to lambda into E. Remember this equation, okay? What we are going to, we have to transform A into A cube. We're going to multiply A by both sides. So this is going to become A squared E is equals to lambda A E. Okay, this is what it's going to become. And now we can see that this over here is equals to this. Okay, same thing, right? Same thing. We're just going to shift it with this. We put A square E is equals to lambda multiplied by lambda E, which will just give us A square E is equals to lambda square E. What we're going to do is that we will multiply A with both sides again. So it's going to become A cube E is equals to lambda squared AE. And once again, we are going to substitute AE with lambda E. So it's just going to become A cube E is equals to lambda cube E. Which goes to show us that for a matrix that is A cube, it will have an eigenvector E for which the eigenvalue will be lambda cube. Was everyone able to understand that?